All right, sir.
Okay, sir.
All right. And he made me aware that you guys have done the unit 1, and now you're on unit 2, and you're on the section 3, right? That's the linear momentum and collisions, meaning you've done the laws of motions and work, energy, and power, right?
Yes, please.
Yes, please.
Okay. So starting with the linear momentum and collisions, that's what we are going to start with today's lessons. Or you've started that one already?
No, please.
Okay. So meaning we move on to page 85. Okay. So we are starting off with the linear momentum and collisions. Okay. To my understanding, before done physics 101 and 102, I guess, or 1 year.
We did physics 2.
What of physics 1? General physics 1.
No, we started with physics 2.
Anyways, they all have a portion of all this in that at least you are familiar with, because you are all physics students, right? So if you talk about momentum, I hope you all know what momentum is, or it still needs a little explanation. Please, this is how we are going to do it. It's an interaction. I ask, then you talk, so that I know your understanding based on how I'll go by it. But if I talk and you're not giving me a feedback, I will assume you know. So I'll just brush it off. Okay. So if I ask, please feel free to talk, or if there is any question, if I'm talking and you have any question on mind, you just come into the conversation and just start speaking. If you start speaking, I'll just hold on for you to put across your question. I hope it's clear.
Yes, please.
Okay, sir.
So if I ask a question or if I ask something, feel free to talk. I'm always listening to your opinion so that I know how best you can all get the thing done. I hope it's clear.
Yes,
Yes, sir.
please.
Yes.
Okay. So as I said, if you say momentum, how do you understand momentum? That's from the general physics we did from the first block. If you say momentum, or generally, if you hear of momentum, what comes in mind?
Sir.
Yes.
Okay, I know momentum is the product of the mass and velocity of a moving object.
Okay, that's perfectly correct. So if you talk about momentum, we are talking about the product of the mass and velocity of any particle. So, for example, if we have, let's say, for a car to move, it requires some momentum. And what is the momentum? It depends on the mass of the car and also the velocity at which the car is moving with. Okay, but then what really have impact, or what really affects momentum of a body is its mass. And why are you saying its mass? Assuming if you apply a force to your body and the force is having a velocity of, let's say, 50 meter per second, right? If you apply this 50 meter per second to, let's say, a 5 kilogram ball, the rate at which this ball will move will be different from if you apply it to a body having a mass of, let's say, 1,000 kilogram. I hope you all understand that.
Yes, sir.
Yes. And that's why I don't know if you've heard of this thing before, that those heavy or heavy duty trucks, that big cars, I don't know if you've heard it before. Almost say sequence and the break in time there, papa. So if you cross him or Yamu and those kind of things, I don't know if you've heard those things before. And it's simply because those cars, because of their mass, they are very heavy. So it requires a very high momentum for it to start moving. And hence, if it has to stop, it requires a very huge brakes before it can stop. Okay, as compared to the small cars. Small cars, because their mass is not that huge, any small velocity can really move it. And that's why if you take the big cars, they are just as many as 16 or whatever, but these small cars has yes, that goes as high as 6 and 7. You get, because the mass they carry has a very influence on their momentum. And that's what we have to talk about. But then this momentum we are dealing with, we are talking about it in only one dimension. In only one dimension. If you say in only one dimension, you mean in a linear form, whether in the x-axis or the y-axis or the z-axis. So we are talking about it in a linear form. It means it's moving in a straight line. So momentum of a body moving in a straight line. And that's what this topic is really going to talk about. I hope you are good.
Yes, please.
And please, as I said earlier on, it's an interactive section. So make us now feel free to draw my attention and let me go back and address whatever you find it difficult understanding. I hope you're good.
Yes, sir.
Okay. So starting off with the section 3.1, which is momentum of a particle. Now, momentum of a particle basically is what is we are having over here. And that's what you guys said, saying is a product of mass and velocity. And yes, momentum is basically the product of mass and velocity. And each unit is what? Kilogram meter per second. Why? Because mass is having the SI unit of kilogram, and the velocity is also having SI unit of what? Meter per second. So when you add these two together, we call what we call kilogram meter per second, and that's the unit for momentum. Are we good?
Yes, sir.
Okay. Now, I don't know if you guys really remember your Newton's laws of motion. Do you remember that?
Yes, I can remember.
Yes.
Okay, so what does the second law says?
The rate of change of momentum is directly proportional to the force applied, and it takes place in the direction of the force.
Very good, very good. And that's what we have over here. Okay. So this is the force we are having. And we say the force is proportional to what? The rate of change in momentum. And you know when you are talking about rate, you are talking about the rate the change in something respect to time. So if the rate of change in momentum means the change in momentum with respect to time, that's why I have the P over dt. So generally, this is the expression based on Newton's law, how we find the momentum of anything. And with this, that's where we get the impulse, we get the inertia, and also we get our general force, which we have as what is called to ma. Okay, and how do we get that? So from here, we say force is equal to the rate of change of momentum with respect to time. So our F is what we have over here. But we also know that momentum is given by this expression. Okay, so if this is momentum, then it means that force can be written as what? And you know, I hope you know if you see d dt, or let me say dy ds. I know you understand that it's the same as change in y over change in s. Do you know that?
Yes, sir.
Yes, please.
Okay, so it means what we have here is the same as change in the momentum divided by the change in time. I hope this is also correct.
Yes, please.
Yes, sir.
So if that is correct, then it means from the equation A, We said momentum is given by what? Mass times velocity. So you have
Change
mv over change.
in time.
Please, I hope no one is confused over here.
Yes, sir.
Okay. Please, if you know Mr. Frank, Mr. Skizo, and yes, sir, yes, sir, yes, sir. So that if you don't even understand, you don't talk. Oh. Feel free. Don't forget about what they will say. Just voice out. Yes, I'm okay. Yes, yes, and then exam soon. I hope you are clear. Frank, what do you I'm off wounding. Okay, please. So if you don't understand, feel free to talk. Forget what Mr. Skizo and Mr. Frank will say. Like I said, and I'll go back to explain it again. Okay. All right. So we are moving on. Now, assuming we say the force is given by the change in momentum of an object. If an object is moving, does the mass of the object changes?
No, please.
Yes, so it means in this case the mass is constant because assuming we say Mr. Frank and I'm gonna say the piano kesia, still the mass now the name or they just my piano the velocity is what to just change. So in that case, the mass is always treated as a constant. I hope you are clear.
Yes, sir.
Okay, so in that case, this expression still becomes the m because the m is constant. Then you have our change in v. Then we divide it by the change in t. And that's what we still have over here. Are we good?
Yes, please.
Yes, please.
Okay. Now, if you are good, what is the definition for acceleration?
Changing velocity.
Changing velocity with time.
Change in velocity with time, right? It means if you have this, it's the same as what? Acceleration. Is that true?
Yes,
sir.
please.
Then it means,
Yes, sir.
it means the expression you are having over here is the same as A.
Yes.
Hence, the F is equal to what?
Okay.
Times A. And this is how come we have the second law they always quote as F is equal to MA. And that's what is done over here. Are we good?
Yes, please.
Yes, sir.
Okay. So that brings about this equation. And also, we know from kinetic energy and potential energy, that's the total. That was what we treated before even this one. Means we did that last week. That's if you are talking about the total energy of a system is given by the summation of the kinetic energy and the potential energy. And I know they went ahead and stated that the potential energy is given as mgh and the kinetic is given as what? LV squared, right? Yes, and that's what we have over here. Now, how did they get this whole expression? And that's what I want us to go through. And I say,
Let's go through, please.
it has quiz. Okay. So from here again, okay, you said this is giving us what? The change in momentum. And MV, we have MV, right? Assuming we say momentum is giving us MV. Okay, and that's what we have at the top here, equation A. Momentum is MV. Now let's square both sides. Okay, so if you square both sides, it means you are going to have P squared is equal to M squared and then V squared. Are we okay?
Yes, sir.
Okay, if this is true, and want to get it in such a way that instead of writing the MV in the kinetic energy, we want to put the P there, then means we have to find a way of making this expression at the right hand side look like what? Hey,
Sir, please come again.
I said, let me
Mm.
change the color of this. I said, now we said we square both sides. Now we have P squared is equal to M squared P squared, right? And we
Sir.
want it in such a way that what we have over here, the momentum squared here, will look like the MV squared we have over here. So what do we do?
We'll divide both sides
By what?
M.
Yes, so we divide here by M, we divide here by M. So that this M will cancel the square over here. And if this is cancelled, it means we have what? MV squared, and that's what we have over here. Okay, it means the MV squared is the same as P squared over M. Is this true?
Yes, sir.
Please,
Yes,
are you all
please.
following?
Yes, sir.
Okay. If this is true, then means instead of writing the MV squared, we can write the PV squared in place of that, so that the K, now instead of writing it as half MV squared, the half is still constant. So we have 1 over 2 into bracket. Now the MV squared is given as what? P squared over M. Okay. And you and I know that 1 times anything is the same as that same value, right? And as this can further expanded as P squared over 2M. And that's how come they had this expression. Are we good?
Yes, please.
Yes, please.
Please take note of this. You really need it when you are doing quantum mechanics and I think classical mechanics. So take note of it. I hope you are good.
Yes, please.
So when you are doing that, then they ask you to derive how kinetic energy is given by this, or they ask you to prove that the Schrödinger time independent equation is given by that. It wouldn't be an issue.
Okay, sir.
So from there, we move to the principle of conservation of linear momentum. We move to the principle of conservation of momentum. But then this linear momentum and collision aspects has to do with collisions. And I hope if you talk about collision, I'm not talking about collision in physics. The English word collision, if you say collision in English, how do you understand it, please? Any idea? Not in physics or in English, come skills. If you say collision, what does it mean?
Head to head.
What is head to head? Let me understand that.
Like something hitting another thing or coming together, having contact with something.
Yeah, so when 2 things crash or something, we are talking about collision over here. Okay. And if collision happens, we have 2 main. Yes. Okay. If there's collision, we have 2 ways of describing them. Of which the first one is say either it's elastic collision or it's inelastic collision. Okay, and those are the 2 types of collision we have, or 2 ways of describing collisions. And with the description, we have to talk about them, or we decide whether it's elastic or inelastic by the conservation of energy, momentum, and also conservation of kinetic energy. And that's why we are speaking about momentum, and also we have done about kinetic energy, so that when we want to define or is to test whether a collision is elastic or inelastic. It will guide us. I hope you are good.
Yes, sir.
Okay. So for the conservation of linear momentum or conservation of momentum, it's always talking about okay, fine. If you are talking about conservation or if you see conservation, what do you guys understand by that word? Not in physics, in English or com skills. If you say you are conserving something or in the process of something, we ensure conservation. What does it mean?
Maybe to protect it.
Protect it. Okay. Protection in English word is correct. What again?
Using something wisely.
It means what?
Using something wisely or judiciously.
I don't get it.
Using something wisely. If you want to
Yes, using
conserve
something
something.
wisely.
Yes.
Using something wisely, that is also accepted. Now, let's apply this understanding in momentum. If we say momentum is conserved or conservation of momentum, what do we think it means? Okay.
That means we are protecting it or we are preserving it. We are
Okay.
preserving the momentum or we are efficiently using the momentum, not overuse. So efficient use of is it.
Okay, it's not a bad try, but then I'll take it. Okay, but then when you talk about conservation, we are trying to talk about the fact that at the end of the day, everything that we need is being protected. There's no loss in that thing. So assuming I have 50 cities and I say, oh, this 50 cities, I'm conserving it to the end of January 2026. It means at the end of January 2026, I should still have my 50 cities intact. I hope it's clear.
Yes, sir.
Okay. Now, if you are talking about conservation of linear momentum or conservation of momentum, it means in that system, and we also say momentum has to do with what? Well, moving objects. And we are also talking about it in terms of collision. So assuming two bodies collide, and we say the conservation of those bodies, the momentum of those bodies are conserved. What you are trying to say is that at the end of the day, the momentum before they came with the collision is the same as momentum after they collided, after the collision. I don't know if I'm making sense or I'm confusing you guys. It means the system occurred in a closed system or isolated system. And when you say a closed or isolated system, means in that environment or in that system, there is no external interaction to that system. So, for example, if the first body was coming with, let's say, a momentum of, let's say, 10 kilogram meter per second, okay, after the collision, you make sure that the momentum of the body is still 10 kilogram meter per second. I hope it's clear.
Yes, sir.
Okay, and that's basically conservation of linear momentum. So basically, in exams or in quiz, they can ask you still the principle of conservation of linear momentum or the conservation of momentum. So it's simply in an isolated system or in a closed system, momentum is always conserved, or momentum before collision is the same as momentum after collision. And that's basically the principle of conservation of linear momentum. I hope it's clear.
Yes, please.
And in those systems, there is no interaction of external forces. Take note. In those systems, there is no interaction of external forces. It means in that system, there's no influence of weather acceleration, other forces, whatever it will be. There will be no interaction of something like that sort. I hope it's clear.
Yes, sir.
Okay, so that is the the simple or the easiest way to let you understand the conservation of momentum. But if you look what you have here, okay. A race, if no external forces act on a system of colliding objects, the total momentum of the object just before collision is equal to the total momentum of the object just after collision. And that's what we just stated. And this is known as the principle of conservation of momentum. I hope everything is good. Or there is confusion somewhere. Is anyone having any confusion somewhere? Hello?
No, sir. I'm okay.
Okay. Are you all good? Because man, just so damn some are good, we'll just move on. Miss Patience, please go ahead. What is your problem?
I mean, I'm okay.
You're okay. All right,
Yeah.
sure.
Mm.
Hey, please, Miss Patience, are you the only female here?
I'm not sure.
Oh, okay. All right. Hey, hello.
Hello, sir.
Hello, can you guys?
Yes, please.
Sir,
Oh,
we can
okay.
hear you.
Yeah.
Okay, okay, okay. So what we are having over here is just a pictorial view of the linear momentum of a system, conservation of linear momentum of a system. So if you watch what we have here, it stands for the momentum before the collision. And if you are talking about the momentum before collision, remember I told you when you are talking about collision, we talk about two objects. Okay. I mentioned that when you are talking about collision, we are talking about two objects or two bodies. So assuming the first body is what we call the assuming the first body is what we are calling as ME. Hello.
Hello, sir.
Yeah, am I audible? Can you guys hear me?
Yes, please.
Okay, sorry. My network just jammed. Sorry about that. So assuming the first body is called what you A, and the second object or the second body is what you are calling MB. Okay, meaning this and this are coming to collide. So before the collision, we have momentum before collision. That is that momentum of this plus momentum of this, because it's these two that are to collide. So I don't know if you want to find the momentum of them for the A, that's momentum of the body A. Okay, is giving us a mass of body A plus P A. Thank you. We are using U because we are saying before collision. And I know when we were dealing with kinematics, we said always U stands for initial velocity and V stands for final velocity. I guess you've not forgotten that. So always when you are doing collision, you see U. Let's say U1 or UA or U something, that maybe is the velocity before collision. Okay. And then if you want to find them of body P as this body as M, then is UV. Okay. So that if you want to find the total collision, it will be P of A plus P of B. Okay, so that this is the same as MA UA plus MB UB. I hope it's clear.
Yes, sir. Yeah.
And this is just for momentum before collision. This is for momentum before collision. But we said in conservation of momentum, right? The total momentum before collision is the same as the total momentum after collision. Hence, we can also find the total momentum after collision, which is going to be for this side. Okay, so let me put I here so that it will tell us is the momentum before collision. Okay, so I'm putting I here for it to tell us the momentum before collision. Now, if we want to find the momentum after collision, we so that it was the momentum after the collision. So after the collision for A, it's still mass and velocity. So if it's the product of mass and velocity, then means momentum for body A will be ma, and now the velocity will be by what v. Okay. So after they apply that, they are moving with not u again, but rather v. We have ma va. Okay. Then if you talk about the momentum of body B, after have m d and then v b. Okay, hence the total momentum after collision will be P A plus P B into brackets or F, where as I stated earlier that the F stands for after the collision, and this is going to be M A V A plus M D V B. Okay. But as we stated earlier on that conservation of linear momentum states that momentum before collision is the same as momentum after collision. In that case, the PA plus PBI must be equal to the PA plus PBF. Because we said the momentum is conserved. If it's conserved, then before collision is given by this, and after collision is given by this. Hence, whatever is over here must be the same as what you're having over here. And that's what we are having over here. So that the total momentum is conserved, giving us that the MAUE plus MBVUB, this stands for the initial or before the collision, must be the same as MAPA plus MBVB. And that's for the final. I hope we are clear.
Yes, sir.
Yes.
Okay. Please, there was a mistake here. This is not you. This is V. Take notes. This is V. It's not you. I think in the book, the second aspect is MBUB. It's not UB. It's MBVB. So take notes. And that's all conservation of linear momentum talks about. I hope you are good.
Yes, you are good, sir.
Okay. Now there's one thing I need to also talk about. Momentum. Okay. For both elastic and inelastic collisions, linear momentum or conservation of momentum is observed. Conservation of momentum is observed. So take note of that. Both elastic and inelastic collision, momentum is conserved. Okay. Now you have another view also proving for the momentum of a system, and that's what we have over here. I don't want us to go through this, but then it's simple. It's very simple because if you want the force A is implying on B, it is same as what B is also implying on A, just that they are moving in opposite direction. So that FAB is the same as the force A is imposing on B. And it's the same as the 4B is also imposing on A, but they are going opposite direction. That's why I have FAB is called negative FBA. It's not anything different. It's not anything different. So that you can bring the FBA to this side, when you cross the equal sign, it become positive. And that's why you have it this way. But note, from second law, we said force is what? The rate of change in momentum. So you have dPA over dt. And that of this one is also give us this. And when you go through it, it gives you the same thing, which is also talking about the conservation of linear momentum. Are we good?
Yes.
Madam Rosemond, please, can we go on?
Yes, sir.
I hope everything is clear. There's no confusion here.
No.
Okay. So this is what we just did up here. What we just did here is what is also done over here. So I guess we can still move on. There's this one person I'm looking for. I've forgotten the name. Madam Sally's brother. Is he here? Hello, class.
Yes, sir.
No.
Yes, Madam Sally's brother. Is he here? I've forgotten the name.
Because I don't know him.
Okay, maybe. That's why I'm back class now. Anyways, it's fine. Let's move on. So we have many applications of the principle of linear momentum. Okay, we have many applications, and these applications is not something new or something strange. So with this, I'll leave you for you to read on. It's not anything difficult, and no one will really stress you to define or explain some of the applications. The basic application that we really need is when it comes to collision. But then when we talk about what we have over here, it just helps you to understand the whole principle well. But since everything has been established already, I won't go through this. I'll leave you to read and get to understand it well. All this clear?
Yes, sir.
Okay. Because I want us to finish with collision and spread, then we move on. I don't know if this you need today, but I just wish we can finish and then we move on. Okay. So the third point is also talking about impulse. It's also talking about impulse. And when you talk about impulse, anyone with idea?
Product of force and time.
Product of force and time. Yes, that is very correct. Physics definitions, wow. Formula definitions. Me com scores there. They always me. Actually, assuming I'm a GHS1 student and I've seen the word impulse somewhere and I want you to explain it to me. How are you going to explain it? Because I don't know what the product of force and time is. So how will you explain it to me? If you and Obian farming kata.
Maybe it would be
Yes.
like the impact that happened after a collision or after a moment happened.
The impact that have happened at a collision.
I mean, yes, how
It
it
is a
happened.
change in momentum.
The
Impulse is a change in momentum.
Yes, that is very correct. But then changing momentum is just saying. It's correct too. It's not wrong. Impulse is the same as changing momentum. Yes. And it's the same as force and this because you realize you said the force is giving us what? Changing momentum over changing time. Okay, that's from up there. And we said momentum, so I changed the momentum is the same as changing whatever. So this can also be written as m changing v over changing t. Okay, and changing v the same as you know, changing v the same as v minus u, where v is the final velocity, use the initial velocity. Okay, and you can still go ahead and expand this as m into bracket v minus u all over changing t. Okay, and this can also further be expanded as mv minus mu all over changing t. Okay, and this is the same as a force. Okay, it means this force times the change in time is the same as the change in momentum, which is the same as mv minus mu. And this is what we call J into brackets impulse. Okay, this is what we call impulse. And that is why whatever you guys are saying is correct, because impulse is the same as the product of force and the time, and the same as what? The change in momentum. Perfect. But I want you to try and explain it to a kid, class 6 or GHS1 student. Okay, so that at least when this child is growing up, you get to know that, oh, okay, say physics crying, yet baba and I say any formulas in it's part of our everyday activity. So as we say, some BBS near Kase impulse na the any day, but the impulse that okay was very huge or something. How will you explain it for such a small child to understand it? Say they are ancient in physics here. It's from that's what I want to hear.
Okay, so impulse, I think acting without thinking about it.
Huh? Is it?
Thinking about it. That is the English definition.
Is that the what?
Acting, doing something without actually looking at the consequences.
So as we said, collision BSc and BBSc. Maybe say impulse then impact how are you going to explain that to that small person or small girl or small boy? Yes, impulse in the
Okay. I want
and
to
I'll
say
leave
that
it for
maybe
you.
the intensity of what happened. Let's say somebody knocked somebody. Maybe a man knocked a woman with a blow.
Mhm.
The intensity of the blow, was it a heavy blow or was it a light one? So that could be the import, the intensity of it. We want to know how
Uh,
the impact of the blow that the man knocked the woman.
So I
okay,
want to
that
So I
come
don't know.
I will take it, but not fully. Any other idea?
in. So I have an idea.
Okay, go ahead.
Can we say it like this? Impulse is, for instance, we know force is a pull or push. So let's say how strong a push is or a pull is and how long it lasts.
Yes, we are getting closer. So, let's talk about the time it took for that thing to happen. Okay, so imagine say, um, uh, no, I won't talk. I won't say this. I'll leave it for you after the. Abi, you go for a break, and I am go break.
So
Yeah, I need a go break,
We'll
right?
go for break.
yes,
What
Uh,
time is the break?
maybe around 2:30.
2:30. About 2 o'clock. Near
2 o'clock.
about time then. 2:30.
No,
Near
2:10.
about 2:10.
Yes.
Okay, then that 10 minutes, I'll leave it for you to think about it well. The answers you all give is okay, but then I still want a
Can I
better.
also try?
You said?
Can I also try?
Okay, feel free. Feel free.
Okay. I also say impulse is the force that causes an object to change its motion. Is that also right?
Um, that is basically uh, uh, I don't know how to say it, but then I won't take that one.
Okay.
Yes, because if you are talking about a force that change the motion or something, it's more or less like defining the same force. Because anything that can change the motion of any object is a force. Okay, but talking about other force changing something means it's serving as external factor that is affecting the whole system.
Okay.
Okay.
Hmm.
So it has to do with
Please, I
the
want to say something.
impact. Okay, go on.
Please, what I'd like to contribute is that an impulse is a sudden action that occurs within a shortest possible time.
Very good. Very good. Okay, that's what basically impulse is. I hope you are good. So if we ask you to define impulse, in terms of physics, formless, now those one is so sometimes try to put it in a way for us to understand it and use the equation or the formula you know to back it up. Okay. Said the way I'm crying almost so but at least so many budget physics almost said physics formulas did baba and those kind of things. No, it's never like that. Okay. Every equation you see has a meaning. And if you get the meaning of that thing, that is what makes physics beautiful. Okay, I hope you are good.
Yes, sir.
Okay, so that is basically yes.
I just want to add my voice.
Okay.
So I can also come from an angle that impulse can be the effect of a force acting for a short time.
Yes. Yes. That is also correct. But then we are always talking about that one. Impulse is also the same as change in momentum. So you can also find a way to explain what it means by when you say there is change in momentum. And that is also the same as impulse. So it's always not one way. It has to do with something that occurs with respect to time or something that occurs with respect to changing momentum. Okay. So it have two sides. Okay. Then we go on and talk about, yes. Okay. Is there any question or we should move on?
Reason move on.
Okay. Now I'm reading from this point. I'm starting from here. Read what is over here. Then we come and look at the diagram. Then we move on. Okay. Because the diagram is talking about basically impulse and how do you find impulse when you are dealing with force in the, because when we are dealing with momentum, we are talking about it in terms of one dimension. You realize this is not in that aspect, so you need to also understand from this. Now, a moving particle has momentum and kinetic energy, but does not carry with it a force. Force requires to cause a particle to reduce its momentum. Depends on how big the momentum change is and on how quickly the momentum change occurs. A long collision time results in a smaller force, and a short collision time results in a larger force. So they said a long collision time. Let me highlight this one for you to see. Okay. So a long collision time results in a smaller force. So if the collision occurs for a very long time, it means the force that it was produced is a smaller one. But if it occurs within a short time, then at the end of the day, a larger force is recorded. Okay. There are many examples of the consequences of this. When a parachute lands, he bends his knees to lengthen the collision time with the air, thereby reducing the force he experienced. A boxer rolls with a point to minimize its effect. Now, suppose a particle of mass M moving along a curve C. Now, this is the curve. Okay, the curve is here from P1 to P2. It's located at P1 and P2 at times T1 and T2. Now, from here to here, we say it's located at P1 and T2 at times T1 and T2, where it has velocities V1 and V2 respectively. Then the time integral of the force F is given by means we want to find the force it took from this point to this point. And how do you do that? We just integrate the force moved from this point to this point. And respect to the time at which it should, because we've already stated that impulse has to do with the product of force and time. So if that's the case, we have the force with respect to time, and the time or the period at which this one occurred, that moving from the this point. Let me use it's moved from this point to this point. So this becomes our T1 and this becomes our T2. Okay. So the force moves from this point to this point. It's what we are calling as the impulse, if we want to find the impulse within this region. So we have to integrate the force we have here with respect to the time aspect from this point to this point, but rather not from the total P1 to the P2. I hope you are good.
Yes. Yes, sir.
Okay. And that's what is done over here. So that at the end of the day, if you integrate the force with respect to the time, you get this. And also, we've also said impulse has to do with change momentum. So instead of the F and T, you can also replace the F with the PDT, because you know the PDT is the same as what momentum. I hope you are good. I'm not confusing anyone here. Am I?
Yeah,
Yeah, okay, sir.
Okay. So just this same expression. This same expression. Okay. And we bring it here. Now, mind you, we said force is given as what? That's according to Newton's second law. The rate of change of momentum with respect to time. Okay, so instead of writing the F, we just write the dp dt in the integral aspect here. So the instead of F dt is now the p dt times dt. Now we also stated that the p is the same as mv or m and change in v. Okay, so in that case, instead of the p, you write the mv over the t because the p is the same as mv, and that's what we did over here. I think we did it up where some years we did it over here. So in that case, I'm not confusing anyone. Okay, so instead of writing the p, you put the mv over here, then we bring out the t. And mind you, this dt is there already, so we also bring it there. I hope you are good. Now, if that's the case, this dt and this dt can cancel out. Okay, so that at the end of the day, you have only the t2 to t1 of dmv. So that I have only this. But mind you, the mass is always constant. Because as we say, oh, corners will be piano, velocity in a bit change. But then the mass is still the same mass as I stated earlier on. So the mass becomes constant, and the only thing that changes is the v. We have m and then the change in v. Now, because now we are not doing respect to time, but respect to the rate of change of momentum, and now velocity no, are changing no. Now we have to do with the velocity we are going first and send Pakobe piano. Pakobe piano. What was the momentum that increased? So from the point where we are moving initially with the point where the piano we are quickly and hence it's no more to time, but rather integration respect to the velocity change. So that you have mdv. I hope you are good. I'm confusing you guys.
So, we are coping. It's just a matter like you just go over, please.
Okay. Do you understand to this point?
Yes.
Okay. Now we said from here the t cancel the t. So I don't really have the integral of t2 and t1, which is the same as what? dmv. Okay. Now I also stated that because it's the same object, hence the mass is treated as constant, or the mass is constant. And you know, when you are doing integration and you integrate a constant, you can't it's always treated as a constant because it's a constant already. So it means with this m, you can substitute it out, or you can bring it out of the or in front of the integral sign, so that you have m in the integral of t2 t1, and then our v respect towards the d. Sorry, let me I think I need to create here. Okay. Now we let me write the d here already. Now you realize we brought this m in front of the integral sign. What is left over here? The v. Okay. And this v is telling us that imagine say obi now pushing now. There are they change here the momentum from the no they economy pushing or they account on. So if that's the key thing that is changing over there is the velocity. Okay, so instead of now dealing with it with respect to time, anytime before what the velocity at which that piano from maybe one day increase the coil. Okay, so that instead of now changing from T1 to T2, won't be that, but rather what the V, because velocity is not changing, not the time anymore. So that you have m then integral of V. Okay, but this time around it's moving from V1 to V2. Are we good?
Yes, sir.
Okay. So if you understand to this point, we know for our integration, when you integrate anything, you get integration, they only mean that, so I shouldn't worry myself. So with this, if we integrate this, we are going to get m, then we have our v. Okay. Now from 1 to 2, which is the same as what? The impulse, which is I, which is also the same as F T. Okay. And now this, since this is changing from 1 to 2, it can be written as M into brackets V2 minus V1. Okay. And this is the same as, since the M is constant, you can multiply through with this. So we have M V2 MV2 minus MV1. And this is also known as impulse. And that's what we've done over here. I hope you are good. Please, I hope you are
Yes,
good.
sir. Yes,
Then
please.
this is what we just proved up there. I just wanted us to go through it this now for you to also get it. Are we good? Can we move on?
Yes, sir.
Madam Patience, please, can we move on?
Yes, please.
Madam, Madam Rosemont, please, can we move on? Okay. Wada. Hey.
We're responding. We're responding with emoji.
Yo. So we are moving on. So have to do with importance before and after and the whole thing again. So should you solve this example or we should just move on to condition one? Okay, let's try this example. So they say an object of mass 2 kilograms at a constant speed of 50 meters per second in the northerly direction. An impulse acting in southerly direction slows this mass down to 25. What is responsible for this? And what is the impulse change? An impulse, we said, same as what? Let's look at the first one. This one is talking about the same impulse, but this time around, we're dealing with respect the force and time. We're dealing with it with respect to force and time. So we realize a given the time it occurred, and you just have them and get your force. Now, this one is talking about it in terms of change in momentum. Okay. The body of the object is 2 kilograms. It means in all situations, the mass is still the same. It's still the 2 kilograms. It's constant. But then once we are taking a look at it, it was moving with 50 meters. And then, secondly, the velocity was built down to 25 meters per second. So if you want to find the input, what do? You find the momentum initial and the momentum final. Just do a subtraction and get the response as to the movement of the object. Why is my network gone?
No, sir.
Oh, okay. By the dynamic and okay.
We are hearing,
It was breaking.
but it was breaking.
Yeah.
So I was saying with this scenario, okay, The mass is constant, which is 2 kilograms. Okay. And they say initially it was moving with a velocity of what? 50 meter per second. And you don't know what happened. Something happened, and then the velocity slowed down to what? 25 meter per second. And now they are telling us what is the impulse vector. Okay. Now, if you are talking about impulse vector, they want to know whether the impulse it increased or it's decreased. Because you always know that when you are dealing with a vector quantity, they want to see both the magnitude and direction. I hope it's clear.
Yes,
And
sir.
when you are dealing with collision and those kind of things, the negative are very important. The negative that we get will tell the direction. Okay. So when you are dealing with this collision aspect or collision stars, we normally don't pay attention to the direction in terms of IGK or SYZ. It's always treated as one dimension, okay, or linear. But then the direction we pay attention to is the negative and positive signs. So if we get a negative, we should know the thing is either decelerating or something. And if we get a positive, that should tell you it's either accelerating or something. I hope it's clear. So now, if this was the initial 50 meter per second, and then the final, after the thing slowed down, the velocity was now changed from 50 to 25 meter per second. What will be the initial momentum and the final momentum? So the initial momentum will be the product of this mass and this velocity. That's the initial one that it was moving. So that the momentum first one, P1, will be equal to the mass times U. Mass is to the U we have here is the 50 because that's the initial velocity. Okay. And if you multiply the mass and the initial velocity, that's the 2 and the 50, we get 100 kilogram meter per second, which is going north. And now the momentum is the same, but now this time around, the velocity have changed from 50 to 25. So it's just a matter of multiplying the mass here to this velocity, going to get out what 2 times 25, which is 50 kilogram meter per second. Okay, which is also going the north. By the end of the day, if you want to find the impulse, is the change in momentum. That's the final momentum minus the momentum. Now, what is the final momentum? The final is we have 15 minus what is the initial momentum? That's the 100 minus 100. And I'm going to get what? We get 50 kilogram. What idea that this one tells you? Okay, and it slows this mass. It slows this mass. So it's trying to tell us that the negative that you are getting the impulse that occurred here is slowed the thing down. But I have a case where you can get a positive value for the impulse, and that should tell that it increases the impulse or whatever that you are looking for. I hope it's clear.
Yes, please.
Okay.
Please, your line break from that play. I don't know if you, is it when you get negative or positive? You say what? Your line break. I didn't get.
I was saying it pays attention to the pattern. And please hold on. Hello. Hello.
Hello, sir.
Yeah, and please, let's go for the break now, and let's come back in the next 15 minutes, okay? So that when we come, we just do everything the rest 3 hours, okay?
Okay, sir.
All right, thank you.
Welcome.
Hello.
Hello, sir.
Yes, please. Can we resume now or time on soon here?
As far as
Oh, fra. And they catch on crop for some and start.
okay. So I think we can start now.
Are they all here now?
Almost.
Okay. Come in. Yes. Please welcome.
Thank you, sir.
Yes. Are you guys busy tomorrow? Hello.
Tomorrow, Sunday, maybe after church.
Maybe after church. You guys don't have any lectures after church, right?
Yeah.
Okay. Can we fix another 2 hours for tomorrow after church so that maybe you end here, then we do that one, the talk and let me check. I think talk and angular momentum tomorrow. Is that okay with you? It's just 2 sessions so that I can finish with this, then leave that to 1 hour. So when I'm done with this one, then we call it off today, then that one tomorrow.
Colleagues talk.
Okay, Jai. More decide mom no my babet no be so show.
Yeah, so please talk.
And please, what do you guys say to that?
The place is accepted.
Okay, so we meet tomorrow for 2 hours, then we do the torque and angular momentum, right? But then
So
we are
when
continuing
the
with
time?
it. I don't want to impose anything on you guys. You said after church, so exactly what time?
Mm.
2 o'clock.
Mm.
Are you guys? Are you
Yeah,
all
2 o'clock
guys?
to 4 o'clock.
Okay.
Okay,
What
so
are others still
tomorrow,
saying? Is it good?
since they are not, I think it's okay with them. So we meet tomorrow 1400 to
Yeah.
1600, right?
Yeah. Okay.
Okay, so tomorrow 1400 to 1600. Okay.
1,600.
All right, let's go on with what you've started so that I can complete this aspect and we
Okay.
move on. Okay. So as we were saying, the impulse is the same as changing momentum. So here they found the momentum before the initial momentum. That's the initial momentum and also the final momentum. And then if you want to find the impulses, there's a change of momentum. So it will be the final minus initial, where we have P2 minus P1. And when we did that, we realized we had negative 50 kilogram meter per second. And I said we had negative, which is trying to tell us that the thing slowed down. It means the rate at which the momentum was going, it reduced. It reduced by a quantity of 50 kilogram meter per second. I hope it's clear.
Yes, sir.
So we move on to the example we also have over here. They said a mass of 5,000 kilogram moves in a straight line. Moves in a straight line from a speed of 540. Hold on. Mr. T. Oh, okay. A mass of 5,000 kilogram moves on a straight line from a speed of 540 kilometer per hour to 720 kilometer per hour in 2 minutes. And now they are asking us to find the import developed in this time. So also the time is also constant. The mass is also constant, right? Now the speed is what there is difference. Okay. So what you do is you find the difference. Then if you know the difference, you can now multiply it by the mass. Okay, so that you can find the change in momentum the same as the impulse. I hope we are good. Are we good? Okay. We are the. Are we good?
Sir, please, I don't get this one.
You get this one. You don't get this one.
Yes, I did.
Okay. Let's go through the solution together so that we go through the solution together. So here they give us the mass, which is 5,000 kilogram, and they give us the initial speed, which is 540 kilometer per hour. Okay. And they give us the final velocity as well, which is the final speed, which is 720 kilometer per hour. Okay. And they said this occurred within 2 minutes. They said, what is the impulse? The dot in this time is the impulse. So first, you can do that by finding the change in momentum. Change in momentum. It means initially we have the speed of this and we have the final of this. But mind you, this in what? Kilometer per hour. But we said impulse, or what's the unit for momentum?
Newton meter.
Newton.
Newton seconds.
Newton seconds.
Kilogram per
Kilogram.
meters per second. Kilogram per meters per second.
Kilogram
Kilogram
meter per second.
second square.
Kilogram meter per second is the same as Newton seconds. Okay, because he said it's the same as force times distance. Force is Newton, time is seconds, so Newton seconds. But let's stick to the change in momentum. Hence, it's going to what? Kilogram meter per second, which is the same as the Newton second. Okay. So how do we do this? We first convert the speed. Okay. We convert them to meter per second instead of kilometer per hour, because he said the unit is what? Kilogram meter per second. So instead of kilometer per hour, I have to be converted to meter per second. So first we did the conversion. So with the 520, the conversion is done and they had this. I hope you know how to go by this, the conversion. You did this in level 100.
Yes,
That's
yes.
the first block.
Yes.
Okay. And you do that for the 720 kilometer per hour as well. And the velocity or the speed is going to be 2 times 10 exponent 2 meter per second I. Now the I is telling us the direction, which is in the S direction. That's why you have the I. Now we said impulse is known as what? Impulse J is giving us change in momentum. Okay. Is the same as mv2 sm1. And we are saying m because the mass is always constant. Okay. Now we know our v1 to be this and our v2 to be this. So this is v2, not v1. I know our v2 to be this. So how do you do that? And the mass is 5,000. 5,000 times this minus the 5,000 times this. And that's what is done over. So 5,000 times 2 times 10 exponent 2, which is the same as what? 200. Okay, so you have 5,000 into brackets. V2 is 2 times 10 exponent 2 is equal to 200, because 10 times 10 is what? 100. 100 times 2 is 200. So you have 200 minus. Now, 1.5 times 100 is what? 150.
150, yeah.
150. Okay. So at the end of the day, this minus this is going to give us 50. Okay. And 50 times 5,000 is what? 25. So you have 25, then times 4 zeros. And then this will be the impulse. I hope you are good.
Yes, please.
Okay. Then we can move on to any question.
Yes, sir.
Okay.
Please, the answer given, it doesn't correlate with what we've gotten. The answer given down there's 2.5 times 10 exponent 2. And this one, when you convert it to standard, forget 2.5 times 10 exponent 5. So
This is 5,000 kilograms. You have 5,000. And this is 2.5, 1.5 times 100. So this times this one will give us 0.5. Now 0.5 thousand will give us what? 2.5, no, 250,000. Yes, so there's error in the answer given here.
Okay.
Yes, this is strong. Okay, this is strong.
All right, sir.
Okay. Now we move on to 3.4, which talks about collisions in one dimension. Collision in one dimension. And obviously that is telling us collision that occurs, or the linear collision. Okay. Because when we started, we were dealing with momentum, linear momentum. So if you are talking about collision in one dimension, you are talking about collision, a linear collision that occurs in only just one dimension, either in the S direction, Y, or the Z. Okay. So in the general case, one-dimensional collision between two masses, one cannot anticipate how much gets penetrated. collision. Therefore, the velocities of the two masses after collision are not completely determined by their velocities before collision. However, conservation of momentum must be satisfied so that if the velocity of the particles after collision is specified, then other can be determined. Okay, so ideally, please hold on. Okay. Yes, so when we are talking about the collision, as we stated earlier on, we have two types, the elastic and inelastic. And when you are talking about the elastic, for elastic, both momentum and kinetic energy are conserved. But for inelastic, only momentum is conserved, kinetic energy is not conserved. And why is it that we say in inelastic, kinetic energy is not conserved? We talk about that. And it's as a matter of after the collision, some of the energy are being converted to other forms of energy, and then it decreases the total energy in the system. That some are converted to sound, some are converted to heat, some are also converted to light. And all this accounts to why after the collision, the kinetic energy is not conserved for inelastic collision. For example, if a car hits, two cars hit, obviously you hear a sound, and that sound that occurs is as a result of some of the energy being converted to that sound, and hence you won't get the total energy before the collision occurred. Okay, so let's start with the elastic collision. An elastic collision is defined as one in which the total kinetic energy of the system is conserved. So, as I said, both the momentum and the kinetic energy are conserved. That is, the total kinetic energy before collision is equal to the total kinetic energy after the collision. If the forces of interaction between the colliding bodies are conservative, then the total kinetic energy before and after collision is the same, and the collision is said to be perfectly elastic. Now, consider the collision of two objects labeled A and B. Thus, the objects A and B are having mass MA, and also the B is having mass MB. And now we are classifying this as the mass A and this as mass B. So the mass A is essentially moving with the velocity of UA. That of the B is also moving with and velocity, say UB. Okay. So in this case, MA is moving this way, it's going this direction, and MB is also moving this direction. Now, after the collision, right, this one is coming here, this one is coming here. So after collision, they'll move back to where they are coming from. Hence, the A will now still have the same mass MA, but then the velocity is no more U, but rather V. We've explained this one already. So the body A will move with V, and that of the B will move with VB. So as we said earlier on, conservation of momentum, it means we have MA, UA, which will be the momentum for only this one, right? Then we have plus MB UB, which will be the momentum for this one. Okay. And then the total momentum before collision. And this must be equal to, because you are saying in all cases, kinetic momentum is conserved. So if it's conserved, it means before and after must always be the same. So it must be equal to the momentum after collision of body A, which is MA, BA plus MB VB, which will be the momentum after collision of the mass B. Okay. And hence, if you sum everything here up, it has to be the same as when you sum everything here up. And if this is true, then we say conservation of momentum is obeyed. And yes, in all cases, it has to be obeyed. Okay. And that is for that. And we go on to the, oh, that is what is even done here. Okay. So that the MBV will be the momentum for this aspect, then MBUB will be that for this aspect, which is here. And after the collision, you have MAVA, which is what you have here. And you have MBVB, which is what you have over here. And that is for the conservation of momentum. Now, we also say that when you are dealing with elastic collision, the kinetic energy is also conserved, meaning the kinetic energy before collision must be the same as kinetic energy after collision. And you and I also know that, or we've done it. We did it earlier that kinetic energy is given by what? Half mv squared. Okay. Now, instead of the V, just using the V and the M, we are talking about two bodies in a system. That's MAUA and MBUB. Okay, that's for the initial, and MABA for the final of the, and MBVB for the final of the body. So that if you want to find the kinetic energy for before collision for body A, mass A, or the body A to be half MA. Now the U or the V is not just V, but what? UA. UA squared. Okay. Plus with this, we do same for the B, because they are the two bodies in question or that are occurring within the system. So they have MD UB squared. Okay, and this is for KE or kinetic energy before collision. Okay, and it's given by this. And hence we can find the kinetic energy after collision as well. We are looking for kinetic energy after collision. We have MA. Now, what's the velocity for body A after the collision? Is V. We have VA all squared plus the body B of MV VB squared. Okay. Now, since conservation of kinetic energy states that kinetic energy before collision will be equal to kinetic energy after collision. Means whatever we have over here, yes, whatever we have here, whatever we have here, whatever we have here is the same as whatever we have here. So in that case, since conservation of kinetic energy is obeyed, then this one must be the same as what you have over here. And that is basically the conservation of kinetic energy. And that's what you have here. So this stands for the kinetic energy before collision. And this stands for the kinetic energy after collision. Okay, so in a typical question regarding momentum, sometimes we can give you the mass of body A and the mass of body B, and give you the initial velocities or the velocities before collision for both A and B, and they ask you to find the final velocity after collision for body A and body V. In that case, you first do for the momentum, okay, so that you get VA and VB, which are all parameters that are not known, and also do for that of the kinetic energy. So when you do that, you get two simultaneous equations. Then you solve them to get your VA and VB as well. Is that clear?
Yes, sir.
Madam Patience, please, is it clear?
Yes, sir.
Okay. Okay. So that is that for us. But then, you know, in your students, I'm out for shortcuts. Okay. So going through to use the kinetic energy to get all those things, you can also go by this approach. Okay. So that you are just using the velocities alone, neglecting the masses. And whatever you get, you just substitute in one expression to get whatever you are looking for. And how do you do this? So here they say if the initial conditions, that the masses and velocities are known. So as I said, if you know the initial velocity for body 1 and body 2, but then you don't know the velocity, final velocity for each of them, instead of solving them simultaneously, that's what you find the final velocity. That's you are looking for both the P and the P. Then we have two equations. That's the conservation of energy, the conservation of energy. That's why kinetic energy is two unknowns. That's the V and V. And it is possible to solve it. So as I said, so that when you get the two simultaneous equations, you solve them and get the P and V. But only that the algebra gets very cumbersome because of the square terms in the kinetic energy equations. Yes, because you have the U squared and the V squares, we are going to say the values will become very big and one should have very confused. So how do you do in terms of eliminating this thing? It turns out that when the collision is happening, the relative velocity of the two objects, the velocity of one relative to the other, it's reserved according to the equation you have over here. And this is true. This is true. So that if you have this, you know your UB and your U, just substitute them there. Then you make either V or V the subject. Then you substitute it in the momentum expression. Then you solve whatever you are looking for. Are we good? Please, are we good?
Yes, sir.
Okay.
Even like we'll get one question and try and see.
You said?
If you like, we'll try one question, we'll see the whole thing.
Okay, let me see if there are questions here. Okay. There's one question here. Now they said object A of mass 10m is velocity. Oh no, this is in terms of mm. I had my confused. I guess there's something that will be. Okay, let's just go there. Let's just use that same thing to solve it for you to get understanding. Okay, they said an object A with mass m, which is equal to 10m. He said the mass is equal to what, 10m. But you and I know that the unit of mass is what, 10 kilogram. But here they say 10m. So pay attention to that. Its initial velocity UA. So MA is equal to 10m. Okay. And the velocity UA. Moving initial velocity UA. Collides head on with velocity B. Wait, I'm sorry. So now MB, MB is equal to M, right? And collide with this one at rest. And if it's at rest, what will be the velocity?
0.
0 meter per second. Okay. Now, what are the final velocity? This one will be so. I want to be quite easy for you to understand. Read the mail, I don't want to say confused. Okay, I'm trying to tune it for us to get a simple thing for you to understand. Now, let's assume the M is kilogram. So M is 10 kilogram, right? And MD is, let's say, 1 kilogram. Okay. And let's assume U1 and U is, let's say, 5 meter per second. Okay. Yes. First, say that initial momentum, that's initial momentum. I'm using MOM as momentum. Okay. Must be equal to final momentum. Okay. So that here you have ME UA plus MB UB must be equal to ME VA plus MB VD. Okay. Now what is our MA? Our MA is 10. We have 10. And now what is UA? UA is what? 5. Okay. Plus, now what is MB? MB is 1. Now what is UB? UB is 0 because it was stationary. Okay. This must be equal to Now MA is what? MA is 10. But what is VA? VA is not known, so we write VA. Okay. Plus, what is NB? NB is 1. And what is VB? VB is also not known, so VB. Okay. So that at the end of the day, we get 10 times 5, which will give us 50. Okay. Will be equal to 10 VA plus VB. Okay. Now, you don't know these two parameters. How do you do that? That was what I was saying. One can choose to go through the conservation of kinetic energy. Okay, conservation of energy. And use the kinetic energy expression to also go through these same steps. But then, a baby, a before so. So in order to do this, that's where we stick to what we have here. That's UB minus VA must be equal to U minus bracket VB minus VA. Okay. So when you come here, you said UB minus UA is the same as negative all in bracket VB minus VA. Okay. And if you know this, now you know UB, you know UA. So you can just substitute them here so that UB is what? 0 minus what is UA? 50. And this band will equal to negative VB plus VA. Okay. Now making VB the subject. Okay. VB, we are making VB the subject of this equation. Okay, let's call this, let's say, equation 1. Okay. Now we are making, let's call it equation 2. And we are making VB the subject equation 2. So that VB will come this here. So instead of negative, it becomes positive. Okay. Now this is negative. When it crosses to this side, it becomes positive. We have 50. Then the V is there already. So you have plus VA. Okay. So let's call this, let's say, equation 3. And hence we can substitute equation 3 into equation 1. Okay, so that equation 1 becomes 50 is equal to 10 VA plus, now VB is not given by, it's given by what? All here. So you have 50 plus VA. Okay, so that at the end of the day, we have 50. This is positive. When it comes, it becomes minus 50. All equal. Now VA, we have VA plus another VA, which is 7 VA. Okay. I hope you are following. Hello.
Hello, sir.
I hope
This
you
you
are
are following.
okay.
Yes, please.
So that I have 50 minus 50 is going to give us what? 0, which is equal to 11 VA. And automatically VA becomes 0. Okay. Now you substitute this VA into equation 3. So that from equation 3, VB is equal to 50 plus VA. and then VB will be equal to 50 plus 0, which is the same as 50 meter per second. Is that okay? Is that okay?
Yes, sir.
Okay, and that's what I was trying to talk about. So instead of when you get to this point, okay, instead of going through using the conservation of energy, that's the kinetic energy, half MAUA squared plus half MBUB squared equals to half MAVA squared plus half MBVB squared, and will make the thing very cumbersome. We just skip that steps by substituting in this expression to solve for the U and V, which will make it so easy and simple to get the velocity for both body A and body B. I hope it's clear. And
Yes,
that's
please.
for the elastic collision. Now, with the inelastic collision, after the right, the bodies is still so as here moving this way, and we have another body B here. Okay, moving either this way or stationary or whatever be the case. After they collide, they will all stick together and move with a common piece. So for the M1, U1. So let me is A that we've been using all this one. Let me use A before you get confused. MAUA plus MB VA plus MB VB, and this is the general conservation thing that we know. But mind you, when you are talking about inelastic collision, VA is the same as VB. And why are we saying that? Because we say after the collision, the balls will stick together and move with the common velocity. So that common velocity is telling us that then the velocity of VA must be the same as VB, and it's the same as the V, which is the common velocity they are all moving with. Okay, so wherever you see V or VB, you can substitute the V there because they are moving with a common velocity. So that after the collision, we have MA, then V plus MB, then V. And this can be written as we substitute the V out. So if we substitute the V out, we have MA plus MB. And this must be equal to all what we have over here. That's MA UA plus MB UB. And this is for inelastic collision. I hope I go. Please, are we here?
Yes, please.
Okay, so for inelastic collision, after the collision, they stick together and move with a common velocity. And that's why you have the velocity substituted out and you have the bodies in bracket, telling us that after their collision, they stick together and move with a common velocity. I hope now we can differentiate between the elastic as far as the variation of momentum Or Madam Patience.
Sir.
I hope now you can differentiate between elastic and inelastic collision as far as the conservative energy circulation and momentum.
Yeah. Yep.
Huh?
No problem. Go through.
No, we have
You know, my network
Mr.
it has been bad since today's lesson. So that's what I'm
Charles,
saying.
what of you?
Yeah. The last rating I read is it MB, the thing aside to MB, I don't know. The last part.
The last one.
Yeah, that's it.
So we said this aspect stands for momentum before collision, right? And as we know, for conservation of momentum, initial momentum or momentum before collision must be the same as momentum after collision. Okay. Then we said for inelastic, after their collision, the bodies will stick together and move with a common velocity. So for the conservation of momentum expression that we know the initial must be the same as the final, and the final is MAVA plus MAVB. But now, since they stick together and move with a common velocity, it means the velocity of A is the same as that of velocity of B, and it's equal to what? V, and the V is the common velocity that they are all moving with. So in case of the VA and VB, you can substitute the V here, and that's what we did here. Okay. So wherever we see VA is the same as VB and the same as V, because when they stick together, they move the common velocity. So that the MAVA will be MAV, and that's what over here. It's going to go to the term body or mass V. So VB is mass V. So and then to carry the conservation momentum is by where we know this is given as the momentum before collision. So you can write MAUA plus MBUB. Okay. That this whole expression stands for the momentum before collision. It must be equal to MAV plus MBV. But as far as your GHS as is concerned, since V is common to all sides or in all the expressions, you can factorize the V out. So that when you factorize the V out, you have V into brackets MA plus MB. Are we okay?
Yes, sir.
Yes, and this is the conservation of momentum for bodies undergoing inelastic collision. When elastic, after they collide, they will stick together and move with a common velocity. Are we good?
Yes.
Okay. So from here, let me see if you should solve examples before you come to the coefficient of restitution. This, we've done this already. Let's see if you have. Okay. Let's start the example. The example we have over here, which is talking about inelastic collision. So two objects, A and B, collide and stick together So at any time you say, it's not always that they will tell you straightforward that it's elastic or inelastic. But then sometimes some of the words or the keywords that will be put in the question should give you idea or should tell whether it's elastic or inelastic. So anytime you hear after colliding they stick together, at least you should know we are talking about inelastic collision. Okay. So for example, if maybe I was to test you or it was an exams, I wouldn't bring this statement here. So if it was to be exams or something, this statement wouldn't be there. So that immediately you see stick together, you should know that you are talking about inelastic collision. I hope you are good.
Yes, please.
Okay. So two
Yeah.
objects may collide and stick together, and now they put in bracket a perfect inelastic collision. Object A has initial velocity UA, and object B is initially at rest. And if an object is initially at rest, what is the velocity? Obviously zero, and we know that. Now we seek to find the final velocity B. So we seek to find the final velocity B of the stuck together masses. So the same thing, we first find for the momentum before collision for both body A and body B. Okay, so when you are done, then you know they move together with a common velocity. You just make the subject, then you solve for that. I hope you are good. I hope you are good.
Yes, sir.
Okay. So sometimes they will give you parameters. For example, if it's an exam or something, we will be giving you we will be asking you to find the restitution and all that. And we'll just be giving you values, that's the masses and maybe velocities or whatever. Then we'll be using that one to look for whatever we are looking for. I hope it's clear.
Yes, please.
Okay. I want us to end here. Okay. Then continue tomorrow so that tomorrow when we come, we do the coefficient of restitution. So after that, then we do the angular momentum and torque. Okay. Okay.
Okay, sir. Okay.
All right. Now we've given, I've dashed you, I think, 1 hour 30 minutes. Please use it to read through again. Whatever we've done, just read through and jot down any question that you encounter so that when we meet tomorrow, you just bring it up for us to address it. Okay.
Yes, sir.
Then I guess in the absence of any question, we can close.
Sir, please, tomorrow the time, you said the time is
And they
2
said
to 4.
1400 to 600.
okay.
2 to
All right.
2 to 4.
2 to 4,
Yes.
yeah.
Yes.
Because the 400 is confusing.
You said?
No, because they said brother said 2 to something 400 to this one.
Hello, sir.
Yes. I mean, 1400 the same as 2 p.m. That's why I was,
Yeah.
yeah. Mr. Charles,
Okay,
don't be
Hello,
thank you,
sir.
sir.
confused. Oh. Yes, Mr. Franks.
Please, sir. I didn't start the lesson earlier with you, but we're supposed to do power and energy there before this was. That one has it been given to us as an reading assignment, or that one you go you visit it
No,
some.
I think Mr. Festus will do that with you
Okay.
because he was not able to tell the exact place you guys got to. So
All right.
I guess also you will take over next week. So you will do that, then maybe move to the next aspect as well.
Okay. Thank you, sir.
All right. Okay. Then enjoy the rest of your day and have a nice week. See you tomorrow.
Same to you.
All right.
Hello.
Hello.
Please have they closed? Have you?
Yes, we've closed. We'll come tomorrow to
Newtonian.
2, 2 o'clock to 4.
And
Me
Mr.
measure
Frank,
you.
Mr. Frank,
don't stop.
I say I should not stop. Jerome. Okay. Jerome, I'll
Mr.
call
Uh,
you.
Frank,
Jerome, I'll call you. Eh?
Okay.
Mr. Frank.
Yes, sir.
Bye
The
bye.
earlier lectures we had, I told you to kindly, write.
Yeah. Okay. The Fermat's
Yes,
principle. I'll do that.
yes.
I'll do that.
I didn't get some step. I wanna.
I'll do it and send it to the group.
All right. Thank you,
all right. Thank you. Thank you.
Mr. Red. Are you there? Al Hassan.
I'm not sure he's there.
All right. We'll meet.
It's like I know him before. That is a red.
What center are you in?
I mean, Tamale Center.
And Tamale, did you meet at Sunyani for your practical?
No. Tamale now we meet at Taco.
Hey, far away from here. All right.
Yeah.
Okay.
Terry resembles somebody, one of my lecture colleagues before. He was a part-time teacher.
Okay.
But
Okay.
from
Okay.
Bimbila, if you see me, ask him that question. Whether he have ever been Bimbila before.
By all means.
Thank you.
Thanks too.